Thank you very much, Aditya. Thank you very much for the invitation. I'm very glad to be here, and thanks for organizing this wonderful get-together. I learned a lot about control theory and optimal control and the variance so far, and thank you for being here. So in the next minutes, I plan to talk about collective reinforcement learning dynamics for sustainability economics. And so you could imagine a plot like that. I'll talk a bit about how multi-agent reinforcement learning solves some problems in sustainability economics. But if you take one thing away from this talk, I want you to appreciate that actually we enrich in this talk multi-agent reinforcement learning with a complex system science perspective. And together they are helpful for sustainability economics. And this is just one framing here. It can be climate economics or environmental economics, so that we are not too precise in that. And so I want to start off with the question that is hopefully a motivating one that is not precisely defined, but are we smart enough for the good life? So do we have enough collective intelligence to achieve what we all strive for in one or the other way? And so what this question entails is, on the one hand, staying within a healthy planet, within the planetary boundaries as they are depicted here in their latest assessment. And you see, okay, this is not looking too good. Many of these boundaries are transgressed, like climate change, but it's also not just the climate change problem. It's also about biodiversity, biosphere integrity, land system change, novel entities. So sustainability is more than climate if we're thinking just about the environmental dimension. So we want to stay below an ecological ceiling. That's the one dimension. But on the other hand, we don't want to have no impact on the Earth system because we want basic human needs fulfilled, like food, health, and various others. And so what you see here is the famous Oxfam donut brought forward by Kate Raworth. And this is sort of the conceptual space, the operating space where we want humanity to be in and fulfill the Sustainable Development Goals, the United Nations agenda in that domain, and do so safely away from catastrophic environmental climate tipping elements. So we do not want to test how it is to cross those. And if you look into various kinds of literatures or even just common sense would tell you what we need is urgent and large-scale collective action to do that. It needs to be very fast, very soon. Now we need to act now is something you hear often and often, and everybody needs to be in the boat, like we as individuals, as households, but also our political leaders and the big companies. They need to be doing their share. So how does science? I ask myself, how does science support that? Well, it largely seems to operate on a decision model like that. So we provide knowledge about the problem. So we publish reports like the IPCC and EPBES. We touched upon those yesterday, right? And starting with the limits to growth report, book, paper from the 1970s. So we do more and more on that. And we also propose solutions, like how should it look like, the decarbonization. So we know there's a problem. We also know what to do, but it seems like it's hard to judge because we don't have a counterfactual, but it seems like this is not working too well. It seems still to be a problem. So my claim is there must be something in that decision model itself that you can bring in technology, social media, AI, that is also influencing this collective decision-making process. So this is where we want to focus on. It's not about the natural science problem definition or a technological or institutional solution. I'm interested in the decision-making process in itself. And so the outline then of my talk is, first, we look at these collective action challenges in, I called it here human-machine ecologies, but the essence is that we have humans, societies, interacting, coupled with an environment, with an ecology, with nature, and more also intelligent machines entering that mix. So that is what I mean by human-machine ecology. How we can go about solving these collective action challenges is the second part. And last, I show you, what we find already with some of the early work that goes in that direction. So, collective action challenges in human-machine ecologies. Another concept from the sustainability sphere, the planetary commons, nature's regulating and maintenance services, which require cooperation. And so this is more a legal framework. We're trying to advance the legal framework of the global commons, things like the atmosphere, which is truly, beyond the jurisdiction of any country, with also including subsystems of the Earth system across the 5 typical pillars of atmosphere, hydrosphere, biosphere, lithosphere, and the cryosphere. So this is the typical, taxonomy and Earth system science that are so critical, so relevant for a functioning Earth system that it is a topic of collective action. For example, here the Amazon rainforest is mainly in the jurisdiction of Brazil, but as a kind of the lung of the Earth, so critical that it's is important for everyone, for the whole global community. And that's why a planetary commons. So you can ask, now what's the challenge with collective action? We just do it. Well, in essence, you can spoil or pinpoint the problem down that an individual, an actor, has to pay a cost for everyone, the collective, receiving a benefit. And if the parameters are as such, you are in a tragedy commons prisoners type of situation, which is essentially the conflict of interest between the individual and the collective. So in this very simple model, I'm sure many of you are familiar, to illustrate the tension or to recapitulate that, everyone can choose, or the two agents can choose, to cooperate or defect. And so imagine I cooperate, you would be better off defecting because B is greater than 2B minus C with the parameters chosen. Imagine I were to defect, well then you would also be better off defecting because C is positive and 0 well-being is better than a negative well-being. So regardless of what I'm doing, you would be better off defecting. But the situation from my perspective is essentially the same. So I would also go to defect. So far, so good. Okay, we would defect. But what's the problem? What's the dilemma? Well, the dilemma is that everyone, we both would be better off if we were to cooperate. Very simple, very influential model. So the greed to exploit others and the fear of being exploited by others drives individuals to defection, but collectively everyone is better off cooperating. So what's the solution to that? Well, we need outside central authorities that regulate that, or we need to privatize the land or whatever it is that we're talking about, and then private entities drive their part efficiently forward, and then we can mitigate that problem. The matter problem is that this is not possible for the planetary commons. We don't have that central authority world government, so it's basically anarchy on the planetary scale. But not so fast, you would say, if you're into that literature. Lynn Ostrom showed that this simple model is deeply thought applied to local commons. There, through various mechanisms of reciprocity, actually people manage to not overexploit commons. So the tragedy is not inevitable. Things are not as simple as they seem. in the prototypical model. Human motivation is complex, and the resource systems themselves have dynamics as well that influence their response to human use. And also you could argue centralized authorities also tend to overuse commons, so it's not a perfect solution. So from that line of thought, what we need is bottom-up approaches, decentralized governance, and multiple forms of social reciprocity. But just empirically, this doesn't seem to work fully, right? Maybe we need to invest more into it, how to scale it up, but it is at least not trivial to scale it up to a planetary system. So the last element on the cooperation agenda that maybe some of you have heard about, this idea of cooperative AI, also intelligent, advanced intelligence machines should be able to cooperate with humans, with each other, when that is desirable. And so to summarize the challenges, in my view, that we still face, given the vast amount of research that went into this problem of getting cooperation going and collective action, is the cognitive elements, the cognitive agency. There might be things that are conducive to cooperation or hindering. The environmental context that needs to be looked at. The collective behavior, and underneath all of these three sort of domains of investigation, we want also a dynamic account. Dynamics is very crucial to talk about stability, to talk about resilience, which is a key concept in sustainability. But also if you want to know how long does it take now to get to this desirable cooperation, it's essentially a dynamic question and an important question. And sort of in the middle, I put here good modeling practices, which hints already about the type of solution I'm proposing. Maybe not too surprising that we want to or need sort of what kind of models. That's a driving question for me. What kind of mathematical language do we need that is able to connect and integrate these four domains in a coherent way? So how do we do that? And so I listed here the desiderator again. So we want a transparent and following good modeling practice account of the dynamics of collective behavior emerging from cognitive agency in an environmental context. These are the 5 lists. And so if you look around into the literature, what's out there, how are people trying to do that? And partly also what we have been seen in the previous talks is, well, you can use dynamical systems theory or the dynamic systems models in various flavors. Yeah, then we can go into detail there. But dynamic system models is one branch. Equilibrium-based models, something I try to encapsulate many economic models, optimization models, where the equilibrium is always some fulfilling some target function. And when I'm on target and the assumptions of my model are correct, it's the best thing I can do. And this is this equilibrium perspective. Nash equilibrium in game theory just has it in its name. And agent-based models is sort of another branch of models. Now, if you look at the desiderator and how they map onto these models, I would argue none is perfectly equipped to decide, okay, we do a dynamical systems approach. Because in dynamical systems, and we can argue here, this is very just maybe sort of rough, extreme cases, and there are in concrete ways blends between those extreme cases. But if you have a dynamical system, I would say it's not straightforward to find the agent in that dynamical system and how to think about cognition, about valuation, about perception if you start from a dynamical system. The equilibrium-based models, that's maybe more easy. They are per definition static, although we can argue there as well. And often criticized is this idea of the hyper-rational agency, where often those models are not about reasoning how a decision has come or is emerged within the agent. So it's not about the cognitive aspect. It's just, what would be the optimal solution. And agent-based models, is sort of the very flexible term. A lot of things can be agent-based models, but one more empirical element in one or other disciplines is that they become complex quite themselves. So they can become often quite opaque and not really understandable very easily because you are so flexible to do with whatever you want to do with them. And so the question is how to integrate all of these approaches. And here is the main argument that we have on the one side complex system science and on the other multi-agent reinforcement learning. And complex system science excels with its insightfulness. So it produces a very rich understanding of how cooperation emerges. But the downside is it tends to be a bit simplistic. It often ignores individual level complexity, environmental context. So those are not straightforwardly integrated into that approach, what has been done. Multi-agent reinforcement learning, on the other hand, is doing that quasi per definition. It is a framework combining collectives of individual intelligent agents in changing dynamic environments. Downside is it can become a bit obscure sometimes, highly stochastic, computationally expensive, and sometimes challenging to interpret. So the idea is that we take the best of both worlds from these two to get inside this triangle of different modeling approaches. So just to give you an example of how maybe a complex system science example about cooperation looks like here, the famous 5 rules for the evolution of cooperation summarized by Martin Nowak. And what I want to highlight here is that this notion or this tendency that we can give simple equations that give us understanding under what conditions of benefits and costs and other factors depending on the mechanism cooperation is, for example, stable, or an evolutionary stable strategy to be precise. But this is just I want to highlight just this style of analysis that or the insightfulness this line of work aims to produce. Here, the example maybe from the Marl world. Here, cooperation is, or I would say, very influentially perceived as a sequential social dilemma. So they say, well, we do not want to start with this very simplistic assumption that agents can rarely cooperate or defect. They have to find a policy for themselves that is then in the total overview a cooperative one, but it's not so easy. And this is, of course, in one way more realistic. What means cooperation is not always clear cut. And so one paradigm is definitely those of grid worlds, where you have here sort of a cleaning or a collective resource harvesting problem. And solution approaches are inspired by previous work in the evolutionary complex systems science domain with reputation norms, other regarding preferences, or just influencing others, and also contracts. So this is based on a review. One front here I just want to mention here, I'm not really deeply familiar on what the current state of work is here, and things are moving so fast, but surely language model-based agents is something that, we will see in more or few agent-based models of that type. But okay, given these rather different approaches to the problem, how can we build the bridges? And so this slide has not many pictures, but I find it one of the more important ones of this talk. So we realize our focus here is sort of modeling for understanding. We are not interested primarily that our solutions, whatever we do, can scale to large problems. So this is a problem that is definitely out there, but this is not our focus. Now, there are other methods and other people more thinking more deeply about how this works or how this can be done. And then we realize all models are wrong. Right? There is no true model. This is the essence of modeling. And so this maybe gives us the freedom to say, oh, what's actually the most simple model or low dimensional environment that is still able to capture what we want to capture. And I give you an example in a few minutes. And the second is we control, or control is probably the wrong word here in this audience, but we take care of the stochasticity of the reinforcement learning process. How do we do that? Well, so here is a typical picture of a multi-agent reinforcement learning setting. We have the agents taking actions, exerting on the environment receives or brings rewards and observations to the agents, and then you have this loop of interacting and also adaptation, which learning, changing the policy through a reward prediction temporal difference error. And the key idea of the more theoretical work that we are doing is we perceive reinforcement learning as a nonlinear dynamic system, looking at the learning dynamics, and often implicitly when I say learning dynamics, I think about the deterministic approximation limit that comes from averaging over all the stochasticity from the policies and the possible transitions in the environment, which can also be stochastic. And so you can maybe conceptually view it a bit similar to the previous talk, that you have a deterministic part of your reinforcement learning update and some noise. And we go to the extreme case and start with looking and analyzing the system when the noise is fully eradicated. Not to say that it's super interesting to study the noise on the deterministic part. And then you structurally arrive at equations. So I'm a very discrete person. I work in discrete time. So this is the policy. So the probability of each agent in each state choosing action A. And this is updated by the current policy times the exponent of sort of the strategy average temporal difference error. And one way to interpret that is that the agents learn how to act as having a sort of perfect model of the world. And you might ask, if they have a perfect model, why do they need to learn? Well, basically what this models is the knowledge to action gap that we often see in sustainability. So how, given the knowledge we have, we come to action. And one uncertainty that is sort of inherent in that is the uncertainty about how the other agents in the system change their behavior. So these agents don't make assumptions about that. They say, okay, given the current behavior of everyone, I should go a bit, change my policy in that direction. Everyone will do so, and they reassess, and this is how the dynamics work. And by that, we get conceptually into this triangle of these three types of models. But this is essentially also not a new idea. It builds upon a interdisciplinary but somehow scattered foundation in different communities, from machine learning to mathematical biology, with different research goals regarding the role of equilibria and biological plausibility that these models should entail. And so really our focus is the nonlinear dynamics of biologically inspired learning of cooperation. So what do we find? And this is a part in two parts, basically. In the first part, we look at what can MAL offer to complex system science, and offering ways to formalize cognition in various contexts. So this goes to the cognitive agency part, the collective behavior, and the environmental context. And so here are some pictures from more AI researchers that highlight on a high level this discussion, how reinforcement learning serves as a general prototype model, as we called it here, for intelligent adaptive decision making. And if you look into these boxes, we always have, so this representing one agent, we have actions and observations or perceptions. Perception module is something, maybe there's an internal world model, memories, intrinsic costs or motivations, valuations. So these, just looking at the literature from more of an outsider, these modules keep appearing. This is why I think taking reinforcement learning as a prototype model, really not so much about specificities of algorithm design, valuable here to get at this the cognitive modeling, but beyond this community, I also like reinforcement learning for its interdisciplinarity. It's not just a machine learning method, it also occurs in empirical disciplines of cognitive science, psychology, neuroscience. And here is the famous graph of the Schulze et al. Paper showing how the dopamine neurons in the brain show, let's call it, similarity with the reward prediction, with the temporal difference error, also technically discovered. So this idea of reward prediction, temporal difference error learning, seems to have some generality across different disciplines, which is why I'm thrilled by it to have it in our modeling framework. How can we represent environments and different styles of environments? Basically, what you realize is this idea of a partially observable stochastic game, some technical term here, is a very general model to represent environmental context that almost always have to do with delayed and stochastic consequences. So delayed and stochastic consequences is something that is very challenging to act upon in domains like health, for example. That your long-term health is about delayed and stochastic consequences. So acting now to have good health in the future when we are old is a challenge, or insurance, saving for retirement. These are all about delayed and stochastic consequences. And here I want to show just examples of different styles of environments, of abrupt transitions, smooth transitions, partial observability, spatially. But here just to show, we can also include social environments in this framework, hereby concretely, basically modeling previous actions of agents as the environmental states. So this is a coherent way to include sociality in this framework. And the collective part, the collective cognition, if you will, well, this is just to highlight, we have a lot of flexibility here. We can think about anonymous relationships, some networks structurally linked. They don't have to be the same. They can have different actions, different roles, up to hierarchical roles. Challenge here is the curse of dimensionality. The more specific we become, the more untractable it will be. But mean field approaches can help with some of those challenges, not all. So bottom line, we have a quite flexible framework. So now, what can complex system science do for the analysis of multi-agent reinforcement learning systems? So what kind of complex emergent phenomena do we see? And this goes a bit to the dynamics and maybe also the collective behavior in its emergent form. So emergence, I just loosely mean here when properties exist on the collective level that we don't have at the individual. So we will look at those phenomena in an example. So this is a quite minimal stylized model of a collective action problem with individual adaptive intelligent decision making using these learning dynamics in this deterministic approximation limit in some environmental commons with a catastrophic threshold. So the idea is we basically have a public goods type of game, a prisoner's dilemma in the prosperous state, as we saw in the beginning of the talk. And both agents can either cooperate or defect. Applied to the climate, for example, taking upon the talk yesterday, cooperation would be abating and defection would be the business as usual emission scenarios. And so given just the prosperous state, we have the same dilemma as before. Everyone would go for defection, but everyone is better off cooperating. But now defection is not only socially suboptimal, it also comes with a risk of collapse. So each agent defecting increases the probability that the prosperous state transitions, collapses to a degraded state in the next round, where we try to make as little assumptions about the reward structure. So we say the agents just suffer in this degraded state, regardless what they do, with a collapse impact M, which is a free variable or one variable. And only eventually, with some time on average, they recover with a recovery probability back into the prosperous state. So that's the model. So not too complicated, even simpler than the 6 equations we saw yesterday. But despite the simplicity, we find sort of the 101 of the nonlinear dynamics phenomena in this model. As we see multi-stability, we see abrupt transitions, hysteresis, and different dynamic regimes. And I want to go through them now briefly. So here is a typical plot you can calculate and plot from these learning dynamics. So here we see on the x-axis the probability of agent 1 to cooperate in the prosperous state, and on the y-axis the same thing for agent 2. So now these arrows here indicate the flow of the learning dynamics, but actually if you look at the edges, they go beyond this probability space, and this is not an error. This is by intention, because these arrows actually represent the temporal difference error, the average temporal difference error that we calculated. So they have a interpretation that we can utilize them in these flow plots. And so what you see here is in these blue trajectories. So this is how the learning evolves in the policy space. And so if they start here with one agent not so cooperative, the others very much, they eventually learn to cooperate. But if they are just a bit over this purple line, over this separatrix, they go to the other line. They go to the full defective scenario. So we have multiple forms, we have mutual cooperation and mutual defection as possible Nash equilibrium solutions. And so just this form of multi-stability has been argued about as a measure of collective intelligence, or to be precise, the basin of attraction, as it's called in dynamical systems. So the size of this basin where cooperation is the attractor as a measure of collective intelligence. It also is some form of emergent collective memory, because you can think about the collective encodes here one bit of information, whether or not they are defecting or cooperating. We also argued it's a geometric view for ad hoc teamwork, and the idea is imagine we are in that equilibrium, and then agent one gets replaced by another one, where we don't know the initial policy, but we see regardless where they are entered, it seems in this situation, they would also learn to cooperate. So we are can be confident that, okay, they could switch team members when the basin of attraction looks like here. And another conceptual link is that in sustainability, social ecological systems science, the basin of attraction is also linked to this idea of resilience when we have stochasticity around an equilibrium. And so the larger that basin of attraction, the more resilient the solution is. So many conceptual links to the simple fact of multi-stability. If we now zoom in into this trajectory bundle next to the separatrix and look at the time evolution. So now we have the two closest trajectories that then end up in cooperation or defection over time. This is a kind of an arbitrary time scale here. It seems like they almost converged after 400 years, after 400 time steps. So if I'm not aware about the geometry of that situation, I might think, okay, well, I should stop the simulation. But then eventually they go apart very drastically. So you also see kind of an emergent separation of time scale here, and can also view that as a transient tipping behavior where it's relatively fast, then stable, and then fast again, but to different consequences. And the last element about multi-stability, now we imagine that agent one starts across this whole, the full line here depicted in orange. And we look at how long does it take when that the agents converge. Then we find at this separatrix point, or at the tipping point, if you will, it takes much, much longer than when you are far away of it. So there's a so-called critical slowing down at the social tipping point here. So the social tipping point is sort of emergent, whereas the ecological is embedded in the model. And if we are at such a social agental tipping point, maybe then guarantees of convergence become less relevant because the time it takes is so the time scale we need this convergence is much shorter than the convergence actually happens. And so this focus on transient learning dynamics maybe is more important. And there's also an opportunity to think about early warning indicators when we are at these critical thresholds. Well, the same conclusions basically translate to if we are now not within a policy space, but move in one community would call that hyperparameter, like parameters outside the model, or model parameters in another community. Here exemplified with the discount factor on the x-axis. So the more the agents care for the future, we get to this transition from defection to cooperation, and at the transition period, it takes much longer than when we are in one clear regime. We also find hysteresis. So hysteresis essentially means history dependence. And here, in contrast to the previous slide, we stay within the simulation while some parameters change. So the agents are in the environment, and then they become more and more patient. They care more and more about the future. So the way to read this plot, size and color indicates time. So they start with a discount factor of 0.6 and then become more and more patient until this first critical point is passed, and they then suddenly learn to cooperate. And then the hysteresis part is, if now the maybe campaign for more far-sighted valuation ends and people become more focused on the present, they remain at the cooperative equilibrium. So in this part, it depends on where you start, whether you defect or whether you cooperate, or the collective. Until, of course, it's not without limits. Another critical threshold is passed, and then they would defect again. And this is another form of collective memory that might be able to be utilized. It's important to maybe bring this idea of tipping elements also to the social domain, and just exemplary here, a sustainability intervention. So the last complex systems phenomena I want to highlight, and it's also the most researched and discovered, is the one of multiple dynamical regimes. But it turns out in the environment, in the game, in the model that I showed you just now, this is not as easily observed, or we didn't discover it. So we change environments to the memory one prisoner's dilemma. So here you see a standard prisoner's dilemma, and they learn to defect. Okay, that's nothing too crazy, nothing too interesting. But if you embed this game into its social environment, so that basically the states, the environmental states is now the social environment encoding what did we do in the previous round. So you then have a both cooperated, both defected, or one or the other cooperated and defected state. And then study the learning dynamics in this situation, you find that they can learn to cooperate as predicted in equilibrium game theory. But you also find these funny oscillations and somewhat unpredictable dynamics. So that you get oscillations and chaotic behavior, as I said, has been found many times. But this is, also just to re-emphasize that this is what can happen in these quite simple learning dynamics. Okay, this brings me to the end of my talk, and it's a bit of an advertisement block. The first, and this is more to acknowledge who I mean by we. So most of the things that I was talking about is in this perspective paper in press in PNIS for almost a year now. So I cannot say when it will be out, but we're all looking forward to that. And yeah, we have a great group of colleagues and thinkers with whom we discuss that. And what I want to particularly acknowledge is we have, the more complex systems people and the model people, and try to come together to, find where's the commonalities, where are the points that we can learn from each other. If you want to start playing with that, there is a Python package, work in progress, that makes these ideas more or less practical. Any feedback on that is much appreciated. And what I spent working on the past 2 years is more a course of these different modeling approaches and how they relate to sustainability challenges and human environment interactions. And so this can also be accessed on GitHub. And so this is more teaching course material, but any feedback you might have on that is very much appreciated. And so to summarize how complex system science and multi-agent reinforcement learning can benefit sustainability economics questions is to basically conceptualize collective action challenges in human-machine ecologies, trying at this broad level question, why are we not cooperating more towards a sustainable future, given all the amount of information we have already and given the many solutions we have? And what it can offer is a transparent analysis following good model practices of the nonlinear dynamics of the collective behavior emerging from individual intelligence in environmental context. It's a long sentence, but I feel we need all of these elements together. How? By building bridges, by learning from each other, from the different disciplines, complex system science and Marl here. But of course, we can find different words or similar. It's more a trend of analyzing um, um, uh, cooperation challenges. So these, don't take them too literally if you don't like a particular word, or you can say evolutionary game theory is very influential to complex system science, for example, here. And this, drives basically this idea of the deterministic approximation limit, collective reinforcement learning dynamics, and this study of relatively simple, low-dimensional environments that can still be insightful to look for the emergent phenomena of cognition in various contexts. And so with that, I thank you very much for your attention.
Thanks very much. I have two questions. First is there any intuition you can offer us on where the bistability comes from when you have this catastrophic kind of events that you add in there? Like, why does that create this particular? Maybe you mentioned and I phased it out of my brain already, but
You basically, I mean,
because you have, as understood it, normally you just have a pretty stable, everyone defects situation, but because you add the catastrophic probability center transition, you get this the phase plot on the left, right?
Yeah,
so
exactly.
So why is this? What is this catastrophic event actually doing to the system? To create that
we can understand that very well. So in the paper where we introduced the environment, it's a 2020 paper. We look at more from the equilibrium perspective, and there you can calculate that the collective incentive regimes change when there is enough punishment or enough caring for the future. Essentially, it's cooperation comes about through punishment. Either your peers punish you if you're not behave, and here sort of the environment punish the collective. And so if we are all going to suffer very much if we don't behave, then yeah, probably there's good reason to behave. And the interesting thing from the equilibrium perspective is, which essentially explains this hysteresis behavior, that we go through, we have this tragedy prisoners dilemma regime. We have a coordination regime where mutual defection and mutual cooperation are stable, but we also find a harmony or comedy of the commons regime where only cooperation is stable and defection is no longer stable. So we find these three regimes in the equilibrium world, but they essentially then give rise to these plots here on the lower left, to these three plots. Yeah.
And thank you. And my second question is, especially for this kind of tipping points and kind of some social phenomena, is there any kind of data you can kind of compare these kind of models to? For example, more isolated communities of like maybe people really into Warhammer or something, and they suddenly really all start hating one thing in this particular social context or something.
Yeah, so I mean, I think this is growing, ongoing research, and then we're also, applying also the data-driven methods from the natural science to social phenomena. And so I imagine reading, remember correctly, reading something about energy transition, and look at uptake of photovoltaic, for example, and whether you can see some critical slowing down phenomena there. And but also online communities is a natural, fruitful place to look for data.
Yeah. All right. Thank you.
Thanks for the nice talk. I think around slide 30, you had these plots where these two trajectories crossed. Yeah. No, forward, maybe 32 something. One more. No, you had not in the phase plane over time. This one, yeah, precisely. this very much looks as if behind this there's some kind of saddle point dynamics. Is that the case?
Yeah, that's basically this. Here should the saddle point be.
Okay.
You have this incoming eigenvector here and the outgoing here, so the saddle is here.
And is that desirable to have these saddle point-like dynamics, or is this undesirable, or does this depend on context?
Yeah, I mean, this depends on what you want, whether or not it's desirable. I look at it more, okay, this is what we find if we come from this model that, sort of was derived from basic assumptions about, how does this simple cooperation challenge model change if we embed it into a dynamic environment? And then, okay, we find that dynamics. I mean, what might be related to that? So in the larger literature on collective risk dilemma and related models, they always do it statically. So they basically say, if we're not cooperate enough, then we experience the punishment of nature immediately. And with those sort of models, it's rarely the case that you would get to this full comedy regime, but still you get a regime like that where you have a coordination challenge, basically. And then the argument is, well, if we need to coordinate on the cooperative solution and we can talk to each other, we can have a climate negotiation and whatnot, then we should be relatively easily go to this cooperative solution. But I would argue in that scenario, it's not guaranteed that we do so, and this has to do with the saddle point dynamic. So I mean, it's better than the tragedy, but worse than if we don't need an intervention on top.
Questions? I was wondering how the dynamics of the simulations and like the stochasticity and the different trajectories you find varies with the number of agents you're simulating. So, for example, if you sort of run the dynamical model for Q-learning with 2 agents, if that's going to be very different from like when you're trying to model like many agents, or because, for example, in evolutionary game theory, you usually assume infinite populations, but as you go to smaller populations, you get like way more stochastic effect and this weird transition. I was wondering how it affected when you model these types of systems. Do you assume infinite agents, like
No,
perfectly smooth, sort of deterministic evolution?
The smoothness comes not from the infinite agents assumption. So you're touching upon this link between evolutionary game theory and reinforcement learning. And the link is that in what is a population in evolutionary game theory is one agent in reinforcement learning. And so the stochasticity in evolutionary game theory, when you go to finite populations, would roughly resemble, so the clear link here regarding stochasticity is not clear to me yet, that the agent has not a perfect model. There's some uncertainty around what to do or how it works, how the world works. And if you utilize another interpretation of batch learning, that you learn about the environment for so and so many times, and if you do that infinitely, you get the smooth deterministic limit. But if you relax that assumption and don't do it infinitely, you're kind of at the finite population. And so finite population would be finite batch, finite, or some uncertainty around the internal model of the agents.
Thanks.
You're welcome.
could ask a question, where do you get the exponent for the TD error? It appears as an exponent in the dynamics. How does that come
That
about?
essentially results from the assumption of Softmax-Boltzmann policy functions.
So, and if one were to have some other policy, not what, how would that
Well,
reflect
then
or-
what you can do is formulate the dynamics in value space. So you would have an equation where instead of x, you have q's, yeah? The q values, the state action values. But essentially, you calculate the strategy average temporal difference error, given any policy, for example, an epsilon greedy policy that results from your q values. But then sort of in dynamical systems language, so the dynamical system state, not to be confused with the state of the environment, the dynamical system state is then not the action probabilities, but the q values. And this is typically higher dimensional than this one. And so, yeah, depending on your use case, this is helpful or not. So, I mean, with these, the visualization is easier, especially if you just have two actions, then you have these nice two-dimensional plots for two agents. But sometimes it's because we are interested in, and we also did that, looking at the effect of epsilon greedy policies. And then we can formulate the dynamics in Q space and maybe not look so much in these flow plots, but nevertheless, also the Q space can offer insightful geometrical insights. Insightful insights. Yeah.
maybe I can ask another. You also have some work on the role of noise and how it can increase the basis of attraction.
Yeah.
Could that also be seen as an intervention on the world, or how is that? I mean, it's good as an insight, but can it lead to some possible actual benefits in some an intervention that you could do?
I mean, the intervention would be to set the right level of noise, probably, right?
But how does one do that? I mean, it's just an intrinsic property of the agent, I guess, learning, or just a finite, partial observability or something like that. Which is
I mean, I haven't thought about using that as an intervention, but it's a nice prompt. If you interpret the noise as the uncertainty you have about the world, if you have a lot of uncertainty about the world, you have a lot of noise. If you have no uncertainty, you have no noise. You evolve deterministically. Or basically, what's left is only the strategic uncertainty. You could ask, okay, what's the optimal level of knowledge, so to speak? But of course, it would lead to many benefit questions. But yeah, it's an inspiring one. Thanks.
Okay.